Economy of mechanism. Keep it simple. Opening. The security system nobody could audit. There is a particular kind of failure that is not a hack, not a breach, not an exploit. It is a review. A security team inherits a system that has accumulated 5 years of additions, an access control layer that was extended 4 times by 4 different engineers, a firewall rule set that has grown to 1,100 entries, an authentication flow that branches into 17 different paths depending on user type, device status, session context, and time of day. They sit down to audit it. 3 weeks later, they have mapped perhaps 60% of the logic and found 3 contradictions whose security implication they cannot determine without running the system and observing what it actually does, because what it does and what the documentation says it does have diverged at some unknown point in the past. The failure is not that the system is insecure in any specific identified way. The failure is that nobody can tell whether it is secure. The complexity has outgrown the team's ability to reason about it. And a system that cannot be reasoned about cannot be trusted, because the next engineer to touch it, the next edge case it encounters, the next integration it must accept will add to the complexity without any reliable understanding of what was already there. This is what economy of mechanism means as a principle and why it is harder to honor than it sounds. It means that security mechanisms should be as small and simple as the problem they solve actually requires. Not simpler. A mechanism that is too simple to do its job is not economical. It is inadequate, but exactly as simple as the job requires, and no more. The discipline of keeping security mechanisms small is a design discipline. Exercised before the first line of code is written and then defended against the accumulation of complexity that is the natural tendency of every system that survives contact with evolving requirements. Claude Shannon, who built modern information theory, had a phrase for this tendency. He called it security through complexity, and he did not mean it as a compliment. The system that is complex enough to be hard to attack is also complex enough to be hard to defend, hard to audit, and almost certain to contain vulnerabilities in the parts that nobody has examined recently, because nobody can hold the whole thing in their head at once. Economy of mechanism is Shannon's corrective, and Salzer and Schroeder's formal articulation of it in their 1975 paper on protection in computer systems remains one of the most directly applicable design principles in the field. Simple designs are verifiable. Verifiable designs are trustworthy. Everything else is a gamble on the completeness of the testing that has been done so far. The foundation, what simplicity actually requires in security design. The vocabulary of security architecture contains 3 concepts whose relationship to each other defines what economy of mechanism actually demands in practice. Getting these precise is not pedantry. It is the foundation for every design decision that follows. The trusted computing base is the totality of security mechanisms in a system. The hardware, firmware, and software that must work correctly for the security policy to be enforced. It is the part of the system that you cannot afford to have wrong. If anything in the TCB fails, the security guarantee of the entire system fails with it. A bug in the operating system kernel, a misconfiguration in the hypervisor, a flaw in the authentication library. These are TCB failures, and they are catastrophic precisely because they undermine every security property built on top of them. The reason the TCB should be kept as small as possible is not aesthetic. It is probabilistic. Every component in the TCB is a potential source of failure. Every line of code is a potential bug. Every interface is a potential misunderstanding between the component that provides a capability and the component that consumes it. Reducing the size of the TCB reduces the probability of failure by reducing the number of things that can go wrong. A TCB that is 10,000 lines of code has fewer places for a security-critical bug to hide than a TCB that is 10 million lines of code and is correspondingly more amenable to formal verification, code review, and the kind of sustained scrutiny that produces confidence. The discipline of minimizing the TCB is the architectural expression of economy of mechanism. When a security architect decides to handle authentication through a single, well-vetted identity library rather than building authentication logic into 5 different services, they are reducing the TCB. When a developer decides to use a standardized cryptographic library rather than implementing their own AES, they are reducing the TCB. When a system designer decides to run 2 functions in separate serverless invocations rather than combining them in a stateful service that maintains additional state, they are reducing the TCB. Each of these decisions is a compression of the component that must be trusted, and each compression is a reduction in the probability that the trust is misplaced. Stateful versus stateless protocols surface the same tension at the network layer. A stateful protocol maintains context across interactions. The server remembers who you are and what you are doing between requests. A stateless protocol treats each interaction as independent. Every request must carry all the context needed to process it, and the server retains nothing between requests. Stateful systems are often easier to use because they offload context management from the client to the server. They are also architecturally more complex because the state that the server maintains must be managed, secured, synchronized across distributed deployments, and protected against corruption. HTTP, in its original design, is stateless. Every web application that added session management on top of HTTP, and virtually every web application has, added a component to the TCB because session management introduces state, and state introduces the possibility of session hijacking, session fixation, and state desynchronization. The security implication is not that stateful systems should never be built. It is that the state they maintain is a security responsibility that must be explicitly designed for, not a background assumption. A stateless API that requires every request to carry a signed JWT with a short expiration time has a simpler security model than a stateful session-based system with long-lived cookies, because the security properties of the JWT, validity, integrity, expiration, are verifiable on each request without consulting a separate session store. The simplicity of a model is a direct consequence of the economy of the mechanism. The policy standard guideline procedure hierarchy is the governance expression of economy of mechanism. A policy is a high-level statement of requirement. A standard is the specific, measurable implementation of that requirement. A guideline is optional guidance that may help in implementing the standard. A procedure is the operational step-by-step instruction. This hierarchy is designed to be simple at the top and specific at the bottom. The policy is short. The standard is concrete. The procedure is actionable. An organization that collapses this hierarchy, that writes policies that try to be procedures or procedures that try to be policies, produces governance artifacts that are simultaneously too vague to be enforced and too prescriptive to be adapted. The result is exactly the inconsistency that causes different departments to implement NIST CSF differently. The standard is not clear enough to produce a single consistent interpretation, which means the economy of the governance mechanism has been violated. The structural tension, simplicity as a design constraint under feature pressure. The tension inside economy of mechanism is the tension between what security requires and what engineers want to build. It is real, it is persistent, and it is the primary force that erodes simple designs over time. Engineers are generally not trying to create complexity. They are solving problems. Each feature request that arrives is a legitimate problem to be solved. Each solution that is added is locally reasonable. It does what it was designed to do. It does not obviously break anything adjacent to it, and it satisfies the immediate requirement. The complexity is not the result of any single decision. It is the accumulated residue of many individually defensible decisions made without a governing constraint that says, the total mechanism must remain simple enough to audit. The governing constraint is exactly what economy of mechanism provides, and it must be enforced as a design principle rather than applied retrospectively as a cleanup activity. Retrospective simplification, refactoring a complex system to be simpler after the complexity has accumulated, is expensive, risky, and organizationally difficult to justify when the system is working well enough to ship. The time to apply the principle is before the design is finalized, when the cost of simplification is measured in whiteboard iterations rather than code rewrites. The specific failure mode that economy of mechanism is designed to prevent is the security review bottleneck. A system that cannot be audited efficiently accumulates unreviewed security debt. The reviewers can only move as fast as their ability to understand the system. A system that is simple enough to be understood quickly can be reviewed thoroughly. A system that requires 3 weeks to map 60% of its logic cannot be reviewed in any meaningful sense. It is deployed with the hope that the parts that could not be reviewed are not the parts that matter. And that hope is the closest thing to a security guarantee the organization has for those components. The other failure mode is the configuration error that is invisible in a complex system. A firewall with 1,100 rules has rules that interact with each other in ways that no single engineer has fully modeled. A rule that was correct when it was added may be overridden by a later rule in ways that are not visible from the later rule's context alone. An access control configuration that has been extended 4 times by 4 engineers may have permission grants that contradict each other, with the effective permission depending on the evaluation order of contradictory rules, an evaluation order that is specified in the platform's documentation, but not in any organizational document. Simple mechanisms do not eliminate configuration errors. They make configuration errors visible and correctable. Complex mechanisms hide them. Architecture, building for simplicity from the first diagram. The architectural expression of economy of mechanism is the 3-tier architecture designed with clean, simple segmentation at each boundary, and the discipline to resist the gravitational pull toward complexity as the system is specified in detail. A 3-tier web application, web tier, application tier, database tier, is a design that has been in production at scale for over 2 decades. Its longevity is not a sign of conservatism in the industry. It is a sign that the design is simple enough to implement correctly, secure enough to protect the assets that modern web applications must protect, and flexible enough to accommodate the range of business requirements that web applications serve. The security properties of this architecture are well understood. The web tier accepts untrusted input from the internet and passes sanitized requests to the application tier. The application tier executes business logic and interacts with the database tier through parameterized queries. The database tier stores persistent data and is not directly reachable from the internet. Each boundary has a specific security function, and the function of each boundary is simple enough to verify. The temptation that economy of mechanism guards against in this architecture is the addition of unnecessary tiers, cross-tier bypass paths, or additional state maintained at each layer. A web tier that also caches session state, performs partial business logic validation, and maintains a direct connection to the database for performance reasons is no longer a web tier in any meaningful architectural sense. It is an entanglement, and the security properties of the three-tier design no longer apply to it because the boundaries have been violated. The fix is not to add more security controls to the entangled tier. It is to remove the entanglement and restore the boundary, to reassign each function to the tier that it architecturally belongs to, so that the security properties of the design can be evaluated against a system that actually has the structure the design claims it has. Role-based access control in Active Directory is the access control expression of the same principle. The design goal of RBAC is to map thousands of individual permissions to a small number of roles, typically 5 to 10 in a well-designed implementation, and to assign users to roles rather than to individual permissions. The economy is in the reduction of the permission space. An IT department with 50 engineers does not have 50 different permission configurations. It has 3 or 4 roles: junior, senior, administrator, contractor, and each role has a specific documented permission set. When a new engineer joins, they are assigned to a role. When an engineer changes responsibility, their role is changed. When the permission set for a role needs to be updated, one change propagates to all users in the role. The failure mode that accumulates when RBAC is not governed by economy of mechanism is role explosion. Each exception to the standard roles becomes a new role. Each request for a slightly different permission set generates a custom group. After 3 years, the organization has 97 groups in Active Directory, many of which are variations on the same basic permission set with minor differences, several of which are no longer assigned to any user, and none of which can be mapped to any business function without significant investigation. The access review process, which should take a few hours to confirm that users have the right roles, takes weeks because the permission space is too fragmented to reason about efficiently. The correct response is not a larger access review team. It is a role consolidation exercise that reapplies economy of mechanism to the permission design, reducing the number of roles to the smallest set that covers all legitimate business functions. Designing a SIEM's log parsing and correlation layer for simplicity is the security operations expression of this principle, and it is where the principle has the most direct impact on day-to-day operational effectiveness. A SIEM that ingests logs from 50 sources and normalizes them into a common schema, a small number of well-defined fields that every source populates, is a SIEM that analysts can query efficiently. A SIEM that ingests logs from 50 sources and normalizes each source into a slightly different schema, with source-specific field names and source-specific event type classifications, is a SIEM that requires analysts to understand the specific schema of each source before they can query it effectively. The complexity of the schema becomes a barrier to investigation speed. The design principle for the parsing layer is to normalize aggressively at ingest. Every log source should produce events with the same field names for the same concepts. The source IP is always SIP. The destination port is always port. The user identity is always user. Events from different sources that represent the same logical action. A successful login should be normalized to the same event type, with source-specific details preserved in extension fields. This normalization is more work at the parsing stage, but multiplies the value of every query and every correlation rule written against the normalized schema, because those queries and rules work against every source without modification. Tools that enforce economy across the architecture. 4 tools embody economy of mechanism at different layers, and each one demonstrates how simplicity is not a concession to inadequacy, but an architectural commitment that produces security benefits that complex alternatives cannot match. Microservices architecture enforces economy of mechanism at the service boundary by decomposing a monolithic application into services, each of which has a single responsibility and a well-defined interface. The security property this produces is containment. Each service has its own security boundary, its own credential scope, and its own blast radius. A vulnerability in the payment processing service does not automatically compromise the user authentication service, because they are separate processes communicating over a defined interface rather than functions sharing a memory space. The principle is not that microservices are inherently more secure than monoliths. A poorly designed microservice architecture can be more complex and harder to secure than a well-designed monolith. The principle is that when each service does exactly one thing, the security posture of each service can be designed, implemented, and audited against exactly that one thing. The trusted computing base of each service is small, and small TCBs are more trustworthy than large ones. The cost of microservices is the complexity that is removed from the application and reappears at the service mesh layer. Service-to-service communication, distributed tracing, consistent authentication across service boundaries, and coordination of deployments across dozens of services are not simple problems, and their solutions, service meshes, distributed tracing platforms, mutual TLS for service identity, add their own architectural components that must themselves be secured. The limitation is that economy of mechanism at the service level does not automatically produce economy of mechanism at the infrastructure level. The net simplicity benefit depends on whether the service boundaries are drawn correctly. Services that are too fine-grained, each doing a fraction of what a single cohesive function should do, multiply interfaces without reducing complexity. Services that are too coarse-grained are monolith fragments rather than independent units. Serverless functions, AWS Lambda, Google Cloud Run, Azure Functions, enforce economy of mechanism at the infrastructure layer by removing the operating system from the developer's security responsibility. A serverless function has no persistent OS to patch, no long-lived process to monitor for compromise, no configuration drift to detect. It executes, it terminates, and the next invocation starts from a clean state. The security model is correspondingly simpler. The developer is responsible for the function's code and its runtime dependencies. The cloud provider is responsible for the execution environment. The shared responsibility boundary is clean and well-defined. The cost is that the execution environment is now entirely opaque. The developer cannot audit the runtime, cannot configure it at the OS level, and must trust the cloud provider's implementation of the execution boundary. The limitation is that stateless functions are not appropriate for every workload. Applications that require persistent state, long-running connections, or low-latency responses to the same context over time may find the serverless model architecturally inadequate regardless of its security simplicity benefits. Standardized CI/CD pipeline templates enforce economy of mechanism at the development and deployment layer by providing every development team with a single, well-tested security pipeline rather than allowing each team to build their own. The template encodes the organization's security requirements: SCSD scanning, SCA dependency checking, container image scanning, secrets detection, as pipeline steps that run automatically for every code change. No team is responsible for deciding whether their build pipeline should include security scanning. The decision has been made once, implemented correctly once, and the template enforces it at every deployment across every team. The security economy is in the multiplication. One correct implementation replaces 100 variations, each of which might have been correct, but none of which could be verified to be correct without auditing each one individually. The cost is that a standardized template must be maintained as a shared service. When a new security requirement emerges, a new scanner, a new compliance check, a new deployment gate, updating the template updates all teams simultaneously, which is a multiplication of benefit. But it also means the template team must understand the requirements of all consuming teams, and changes to the template that are appropriate for one team's context may not be appropriate for another's. The limitation is that templates reduce flexibility. Teams with genuinely unusual security requirements, a team building for a regulated environment with controls that go beyond the standard template, must either extend the template or maintain their own, which reintroduces the variance the standard template was designed to eliminate. Implementation: designing simple systems when complexity is the path of least resistance. Two implementation scenarios demonstrate economy of mechanism being applied at the moment when complexity is the natural gravitational force and simplicity requires deliberate architectural defense. The first is the JSON-based reporting system for a security data pipeline that must generate daily, weekly, and monthly roll-ups of threat activity. The initial proposal from the engineering team has 3 separate services: a daily aggregation service that processes raw logs and writes daily summaries, a weekly roll-up service that reads the daily summaries and produces weekly totals, and a monthly report service that produces monthly views with comparative metrics. Each service has its own data model, its own storage backend, and its own deployment schedule. The argument for this design is separation of concerns. Each service does one thing. The argument against it, from the economy of mechanism perspective, is that the separation has been drawn at the wrong boundary. 3 separate services with 3 separate data models and 3 separate storage backends means 3 times the deployment complexity, 3 times the monitoring surface, and 3 times the places where silent data corruption can occur before anyone notices. When the daily aggregation service produces a slightly different field schema than the weekly roll-up service expects, the inconsistency does not produce an error. It produces a weekly report where one field is missing or incorrectly typed, and the consumer does not know what the correct value should be because the intermediate daily summary has already been overwritten by the next day's run. The economy of mechanism design collapses this into a single pipeline with a single data model. Raw logs are ingested and parsed into a normalized event schema. A single aggregation function runs on schedule. Daily, weekly, and monthly windows are just different parameters to the same aggregation logic, not different services. The outputs are stored in a single, consistently structured JSON format, whose schema is validated before any output is written to the output directory. The reporting system has one deployment, one data model, one validation layer, and one failure mode to monitor. An error in the aggregation logic manifests identically regardless of which reporting window it affects, which makes it findable and fixable in one place rather than three. The trade-off is that the single aggregation function must be parameterized to handle different time windows correctly, which requires more careful design of the aggregation logic than a hard-coded daily function. That design investment is made once, not 3 times. The second is the Slack notification integration for a security automation pipeline. The initial design sends a notification for every alert the pipeline processes, every new IP observed, every new malware sample analyzed, every threshold crossed. The argument for this design is completeness. The SOC team wanted visibility into everything the pipeline was doing. After 2 weeks in production, the SOC team is ignoring the Slack channel because it generates 700 messages per day, and the 3 messages per week that actually require human attention are lost in the noise. Alert fatigue at the channel level has made the notification system worse than no notification system. The economy of mechanism redesign begins with a question. What decisions does a human need to make based on this notification, and what information does that decision require? A notification about a new IP observed in honeypot telemetry does not require a human decision. The pipeline handles it automatically. A notification about a new malware sample that scored 0 on VirusTotal despite exhibiting suspicious behavioral characteristics does require a human decision. A malware analyst should examine it. A notification about a pipeline failure that caused 3 hours of missing data requires a human decision. The on-call engineer should investigate and restart the pipeline. The redesigned notification system sends 3 categories of messages. Pipeline health alerts when something stops working, high-confidence threat alerts when the pipeline identifies a sample or pattern that meets a specific fidelity threshold, and daily digest summaries that provide a single daily message containing the total activity counts and any anomalies. The Slack channel goes from 700 messages per day to approximately 8. Every message receives attention because every message is actionable. The information density of the channel has increased dramatically while the message volume has decreased by 99%. Economy of mechanism applied to notification design produces a more useful, more attended communication channel, not by adding more information, but by removing everything that does not require decision. When complexity causes failure, 3 diagnostic scenarios. 3 failure scenarios demonstrate what happens when economy of mechanism is violated and what restoring it requires in each case. The first scenario is the SIEM generating thousands of false positive alerts from a detection rule designed to catch multiple failed authentication attempts. The rule fires for every instance of 5 or more failed logins to any system within a 10-minute window. The problem is that the organization's vulnerability scanner runs credentialed authentication tests against every internal system daily, using multiple probe credentials that fail intentionally as part of the scan methodology. Each credentialed probe generates failed authentication events. Across 4,000 internal systems, the scanner generates approximately 30,000 failed authentication events per day, all of which match the rule and all of which produce alerts. The diagnostic begins by examining the rule logic against the population of events it is firing on. Pull a sample of the alerts and examine their source attributes: source IP, account names, target systems, timing distribution. If 98% of the alerts share the same source IP range, the vulnerability scanner's management subnet, the rule has a scope problem. It was written to detect a real threat, brute force credential attacks, but its trigger condition is also satisfied by a legitimate operational activity that was not considered when the rule was written. The fix is not to disable the rule. The fix is to add a scope constraint that excludes the scanner's known activity from the rule's evaluation. An exclusion list for the scanner's source IP range, combined with an exclusion for the specific service account credentials the scanner uses, eliminates the false positive class without affecting the rule's ability to detect genuine brute force attacks from other sources. The exclusion itself is a form of economy of mechanism applied to the detection logic. The rule is now doing exactly what it was designed to do, without doing additional things that produce no investigative value. The deeper question the scenario raises is why the rule was deployed without this exclusion in the first place. The answer is almost always the same. The rule was written and tested in a lab environment that did not replicate the scanner's activity, and the scanner's activity was not considered during the rule design. Economy of mechanism in detection engineering requires testing rules against a realistic representation of the environment they will run in, including all legitimate activities that generate events similar to the attacker activity being detected. The test corpus for a brute force detection rule should include vulnerability scanner activity, password reset service activity, and any other legitimate sources of failed authentication events, so that exclusions can be built in before deployment rather than added as emergency patches after the false positive flood. The second scenario is an OT device, an industrial controller managing a heating and ventilation system in a manufacturing facility that intermittently loses communication with its management system after a firewall rule upgrade. The device had communicated reliably for 3 years before the upgrade. The communication failure is not total. The device responds to ping, and most commands work correctly. Specific configuration commands fail, and the failure is intermittent rather than consistent, which makes it harder to reproduce. The diagnostic begins with the firewall upgrade changelog. What rules were added, modified, or removed? The intermittent nature of the failure suggests a stateful inspection issue rather than a simple allow/deny rule problem. Stateful firewalls track connection states and apply different handling to establish connections versus new connection attempts. A new deep packet inspection rule for industrial protocols, added as part of a broader OT security hardening initiative, may be inspecting the payload of configuration commands and treating certain command codes as connection reset candidates, without the operator who added the rule being aware that the protocol uses those command codes for legitimate configuration operations. Pull the firewall logs for the connection in question and filter for drop or reset events associated with the device's IP. If the drops correlate with specific payload patterns, specific bytes at specific offsets in the TCP stream, the DPI rule is the culprit. The fix is to create an exception for the specific command codes that the legitimate device uses, documented in the firewall rule with the business justification and review date. The rule that caused the problem was not wrong in principle. Inspecting industrial protocol payloads is a legitimate security control. It was wrong in specificity. It was applied without sufficient knowledge of the protocol's legitimate command set to distinguish malicious payloads from correct operations. The economy of mechanism lesson is that adding complexity to a security mechanism, in this case, adding DPI to a firewall that had previously performed stateless packet filtering, increases the probability of interaction effects with the systems the mechanism is designed to protect. The interaction effect here is not a security failure. It is an operational failure that would have been avoided if the DPI rule had been tested against the actual command traffic of every OT device in scope before deployment. The correct process for adding DPI to a production OT network is a change management procedure that requires traffic capture and analysis before deployment, not after. The third scenario is the inconsistency that arises when different departments implement the NIST CSS Protect function differently. The IT security team has mapped Protect to firewall configuration, patch management, and endpoint antivirus. The application development team has mapped it to input validation, output encoding, and dependency scanning. The cloud operations team has mapped it to security group configuration, IAM policy review, and encryption at rest. All three interpretations are defensible. None of them are wrong. But the organization cannot demonstrate that its implementation of the Protect function is consistent across its scope, because the scope has three different implementations that are not mapped to each other. The Diagnostic is a control mapping exercise. Each team's implementation is documented in detail. Specific controls, specific tools, specific measurements. The control mapping compares each team's implementation to the NIST CSF subcategory descriptions and identifies where the same subcategory is being implemented by all three teams consistently, where it is implemented by some teams and not others, and where different teams are implementing it through different mechanisms with different assurance levels. The fix is a standards document, a single internal standard that translates each NIST CSF subcategory into the organization's specific implementation requirement. The standard is specific enough that any team reading it can determine whether their current implementation meets it. The cloud operations team's security group configuration is the organization's implementation of network access control. The standard says so explicitly, mapping the subcategory to the specific control mechanism. The application team's dependency scanning is the organization's implementation of software integrity verification. The standard says so. The IT team's endpoint antivirus is the organization's implementation of malicious code detection. The standard says so. The three implementations are not replaced. They are connected to a common reference point that makes the organization's overall implementation of the Protect function auditable. Economy of mechanism applied to governance is the production of a standard that is specific enough to produce a consistent interpretation without being so prescriptive that it cannot be adapted to genuinely different operating environments. Three roles. Three dimensions of simplicity. Three roles in counter economy of mechanism at different layers, and the specific design skill each brings to it determines whether the principle produces genuine security value or merely aesthetic preference for minimal-looking systems. The security architect encounters economy of mechanism at the most consequential point, the design review, where complexity is proposed and must be evaluated against the simplicity constraint. The specific moment is a design proposal for a file-sharing application whose developers have proposed custom encryption, a blockchain-based audit log, and biometric heat map access control. Each element is individually motivated. The developers have read that standard encryption is old technology, that blockchains provide tamper-proof audit trails, and that biometrics are more secure than passwords. Each element, in isolation, addresses a real concern. Together, they represent a system whose implementation complexity is orders of magnitude beyond what the security requirement actually demands. The architect's job is not to dismiss the concerns. It is to propose mechanisms that address each concern with the minimum complexity the concern actually requires. Encryption at rest with ES 256 and in transit with TLS 1.3 addresses the confidentiality concern with mechanisms that are proven, implemented in vetted libraries, and require no custom development. An append-only database table backed up to immutable object storage addresses the audit trail concern with a mechanism that every database administrator in the organization already understands and every auditor already knows how to query. SSO with 3 roles, viewer, editor, administrator, addresses the access control concern with a mechanism that is already deployed in the organization and whose policy can be verified in minutes. The architect proposes each of these in a document that maps each developer concern to the simple mechanism that addresses it, with a note on what the simple mechanism costs in engineering time versus what the complex mechanism costs. The goal is to make the economy of mechanism recommendation feel like the practical choice rather than the conservative one. The security automation engineer encounters economy of mechanism in the code they write for security workflows at the moment when a working solution is complete but not yet simple. The specific challenge is that automation code tends to accumulate conditional logic as edge cases are discovered and handled. A pipeline that started as 50 lines of Python to parse log files and generate a summary has grown to 400 lines over 6 months, with special case handling for 3 different log formats, retry logic that have been patched 4 times, and a reporting function that produces different output structure depending on which of 7 configuration flags is set. The code works. The code is not auditable. The economy of mechanism discipline for the automation engineer is the refactoring session, applied before the code is deployed to production and after any significant accumulation of conditional logic. The refactoring goal is not to reduce line count for aesthetic reasons. It is to make every code path explicit, every conditional visible, and every output structure consistent. A pipeline that produces different output structure depending on configuration flags is a pipeline whose security properties, specifically whether the output has been correctly validated before being consumed by a downstream process, cannot be verified without testing every combination of flags. Refactoring to produce a single consistent output structure with configuration controlling which fields are populated eliminates the combinatorial space of validation cases. The validation layer needs to check 1 schema, not 7. The security data engineer encounters economy of mechanism at the schema design layer, where the decision made before the first record is inserted will determine whether the data can be queried efficiently, audited reliably, and extended without breaking existing consumers. The specific moment is the design of a threat intelligence JSON schema that will be generated daily and consumed by a dashboard, a CM, and an alert deduplication backend. 3 consumers with potentially different requirements create pressure toward a complex schema that tries to serve all three optimally. The economy of mechanism discipline is to design one schema that is correct for the most common query patterns and let each consumer extract the fields it needs, rather than optimizing the schema separately for each consumer. The specific design choice that economy of mechanism guides is the normalization of nested versus flat structures. A nested schema that groups related fields, all IP attributes nested under a source object, all temporal attributes nested under a timing object, is semantically elegant, but produces queries that must navigate multiple levels of structure to retrieve commonly needed combinations of fields. A flat schema that exposes all fields at the top level is less elegant, but produces queries that are simple, fast, and easy to validate. For a threat intelligence record that will be queried by analysts under time pressure, the flat schema is the economical choice. The elegance of a nested structure does not compensate for the investigative friction it introduces. Case scenario: the application that was rebuilt 4 times. The scenario is a mid-sized financial services company whose internal compliance reporting tool has been rebuilt from scratch 3 times in 5 years. The first version was built by a contractor who left the company, and the code was undocumented. The second version was a rewrite that added a custom reporting engine to address flexibility complaints about the first version. It was abandoned when the developer who built the reporting engine moved to another team and nobody else understood it. The third version used a commercial off-the-shelf reporting platform that was extensively customized with plugins and integrations. It was retired when the vendor discontinued the version the company had customized, and the customizations were not compatible with the new version. The company is now beginning the 4th version. The constraint is that the 4th version must be built by the existing internal development team, 4 engineers, within a 12-week budget window. It must generate regulatory compliance reports for 3 frameworks: SOC2, ISO 27001, and PCI-DSS. It must allow the compliance team to update the underlying control evidence without developer involvement. And it must be auditable by external auditors who are not technical, who need to verify that the reports accurately represent the control evidence without being able to read code. The architecture team reviews the 3 failed previous versions and identifies the common failure mode in each. The first version failed because the design was undocumented and the knowledge was embodied in a person rather than in an artifact. The second version failed because the custom reporting engine was a mechanism of unnecessary complexity. Its flexibility was never used by the compliance team, who needed the same 5 report types in every engagement. The third version failed because the customizations to the commercial platform created a dependency on a specific version of a specific product, and the customizations themselves violated economy of mechanism by adding bespoke logic on top of a system that was already complex. The 4th version is designed from the economy of mechanism principle applied to each layer. The data layer is a simple relational database, PostgreSQL, with a schema that represents 3 tables: controls, evidence, and mappings. A control has an identifier, a framework reference, a description, and a status. An evidence record has an identifier, a creation date, a description, and a reference to the document or system that provides the evidence. A mapping record connects an evidence record to a control record. This schema is 30 lines of SQL. Any database administrator in the company can understand it in 10 minutes. Any auditor who needs to verify that the reports accurately represent the underlying data can query these 3 tables directly and confirm the mapping. The reporting layer generates reports as PDFs from templates. There are 5 templates, one for each report type the compliance team actually uses. The templates are authored in a lightweight templating language that the compliance team can edit without developer involvement, which addresses the requirement that control evidence updates do not require a developer. The templates pull data from the 3-table schema through simple queries that are embedded in the templates and visible to anyone who reads them. There is no custom reporting engine. There is no reporting platform. There are queries and templates. The delivery layer is a scheduled job that runs the 5 report templates on a defined cadence, deposits the outputs in a versioned object storage bucket, and sends a notification to the compliance team with a link to the latest reports. The scheduled job is 40 lines of Python. The notification is a Slack message with a runtime stamp and a count of reports generated. There are no dashboards, no interactive reports, no drill-down capabilities, features that were requested during requirements gathering, but that the architecture team identified as outside the definition of the compliance reporting problem. The 4th version is deployed in 9 weeks. The external audit that follows it takes 1 day, not the 3 days that previous audits required, because the auditors can verify the mapping between evidence and controls by querying the database directly. They do not need to trace data through a custom reporting engine or a customized commercial platform. The compliance team makes their first update to a control template on day 15 without involving a developer, which is the first time in 5 years that the compliance reporting tool has been updated without a development ticket. The architecture team documents the design in a single-page architecture decision record. The record notes that 3 categories of features were explicitly excluded: a custom reporting engine, an interactive dashboard, and framework mapping automation. For each excluded feature, the record states the requirement that motivated the feature request, the mechanism that addresses the requirement at lower complexity, and the residual gap between what was built and what was requested. The residual gaps are small. The compliance team cannot drill down into evidence records from within the report, and framework mapping must be done manually in the database rather than through an automated mapping engine. The architecture team's judgment is that both gaps can be addressed by simpler operational workarounds: a link from the report to the object storage location of the evidence, and a spreadsheet that the compliance team maintains for framework mapping, and that building mechanisms to eliminate them would add more complexity than the gaps justify. 3 months after deployment, a new engineer joins the company and is assigned to add a 4th compliance framework, NIST 800-53, to the reporting tool. She reads the architecture decision record, examines the 3-table schema, reads the template for the existing SOC2 report, and adds the new framework in 6 hours, adding the NIST 800-53 controls to the controls table, adding the relevant evidence mappings, and creating a new report template by copying the SOC2 template and modifying the framework references. She does not need to understand a custom reporting engine. She does not need to read 400 lines of conditional Python. She needs to understand 3 tables and 5 template files. The economy of mechanism design delivers its most important benefit not at the moment of initial deployment, but at the moment of the first change, the moment when the system is extended by someone who was not present when it was built. Closing, the design that proves itself by being understood. There's a test that every security mechanism can be subjected to, and it is the most honest test available. Can someone who was not present when a mechanism was designed sit down with the design documentation and determine, within a reasonable time, whether the mechanism is correctly implemented and whether it does what it claims to do. If the answer is yes, the mechanism is simple enough to be trustworthy. If the answer is no, if the mechanism requires the institutional knowledge of its designers to be verified, if understanding it requires tracing logic through 10 layers of abstraction, if its security properties can only be asserted and not demonstrated, then the mechanism's complexity is not a feature. It is a liability. Economy of mechanism is not a prescription for minimal systems. It is a prescription for systems whose complexity is justified by the problem they solve, and no more. The three-table database schema that the compliance team's auditors can query directly is not simpler than the problem requires. It is exactly as complex as the problem requires, and the precision of that fit is what makes it auditable. The 5 notification categories that the SOC team actually attends to is not a degraded version of the 700 daily messages. It is the version whose economy produces genuine security value rather than the illusion of comprehensive coverage. The discipline of economy of mechanism is the discipline of asking, for every proposed addition to a security mechanism, does this addition earn its complexity? Does the security property it provides justify the audit burden it creates, the configuration error it enables, and the cognitive load it imposes on the engineers who will maintain it and the analysts who will operate it? Most additions do not survive that question honestly answered. The ones that do belong in the design. The ones that do not belong on the backlog, reserved for the moment when the simpler mechanism demonstrably cannot address the requirement. The security professional who internalizes this principle carries a single test into every design review. Can you explain this mechanism to a competent colleague in 5 minutes, including its security properties and its failure modes? If you cannot, the mechanism is not yet ready to be deployed. Build the version you can explain. That version is almost always secure enough, is always more auditable, and it is always the version that the engineer arriving 6 months from now will be grateful to find. End of session. Economy of mechanism. Keep it simple.